Hello everyone, I hope you all are doing well. This side Priya Bhatia. And in this video, we will discuss another amazing concept in machine learning series. So I hope you all remember that in our last video, we have talked about bias, variance, errors basically, right? And we have seen that ultimately our ideal goal is to reduce that bias and variance. We have talked about overfitting, underfitting, at what situation these kind of things will happen, right? So today in this video, we will discuss that how basically we can avoid overfitting. And the major concept regarding the avoidance of that overfitting part is regularization techniques. So in machine learning, this topic plays a very important role. And even when you will apply these things in industry, whenever you will implement the projects, you will observe that this is a very common problem which is happening. And the way to resolve that is by applying the techniques that we will discuss in today's session. So without wasting any time, let's get started. So now, as we have discussed that these techniques will be helpful only when we will be having a overfitted kind of a situation. So let's try to rewind that what is the literal meaning of overfitting. We have discussed although, but let's do a revision first and then we will continue our further discussion today. So whenever we're talking about overfitting, we have seen that, let's say, we have trained our model, right, on a training data, and we got some accuracy. And at the time of training, let's say you will be able to have a very good accuracy, very good number, maybe 90%, maybe 99%. Why 90? Maybe 99.99%. You will be able to get something very, very good number in terms of the accuracy. Or in other words, I can say that your training loss is very, very low. One and the same thing, right? Accuracy is high or the error is very low. One and the same thing. So in other words, your error is, I can say, approximately equal to 0. But when you try to use that model to test, right, in the testing data, you will be very surprised to see that the accuracy drops down. So here it is very, very good, right? The results are very, very apt. But at the time of testing, it drops down to, let's say, maybe 40%, maybe 30%. So it drops down very, very, by a very big number, right? The difference between the training accuracy and the testing accuracy is very, very huge. Means certainly you will be able to observe that error booms up. Error is very, very high. So this kind of situation where you will be having a training error to be approximately equal to 0 and testing error is very, very high. That is the kind of a situation which you can say is a overfitting. That's why in our last session we have discussed that this is a kind of a situation where we will be having high variance and low bias, right? Low bias means low training error, but high variance means the difference between the variation of the training and the testing data is very, very huge. Now, to avoid this situation, first of all, we need to understand that why is this happening? Training and testing error, right? What's the reason? What's the internal reason behind that? To go through that part, let me again try to create a diagram for a linear regression per se that we have learned already. Maybe the same problem. Maybe you will be having a height of a person, and let's say, which is on x-axis. Your task is to predict the weight of that particular person in the y-axis. Now, you have been given data points, which certainly indicates that the distribution of this x and y is somehow directly proportional. And you have observed that you try to make a best fit line. There are data points which are available with respect to these points that we have, right? We have tried to create a best fit line, which certainly is pointing to all the values and is having a minimum error. Okay? Now, when I'm saying overfitting the data, or when I'm saying that at the time of training the error is approximately equal to 0, it certainly indicates that your data points almost lie on the best fit line, right? Your data points maybe almost lie on the best fit line that you have got. This is the best fit line. And let's say whatever be the training data point that you have, it is somehow lying on this best fit line itself. At that point of time only you can see the error is approximately equal to 0, because let's say you will be having this as the actual value, which is y, and the y cap is this, right? Y cap is this. So you can see the difference between these two values is approximately 0. right? Y will be also lying in this part and y cap is also lying on this part. So basically what we have observed is that in this case, we will be certainly able to get the error value as approximately 0. But this is happening for the trained data, right? Now what will happen at the time of testing? It is obviously not a best fit line, because somehow your data point at the time of testing will lie maybe on this point. Error will abruptly increase. So maybe this might be the best fit line, this might be the best fit line, but obviously getting the approximate error as 0, where we are talking about the best fit line, is not the apt one, right? That's the situation of overfitting. Now the question is how we can avoid that. The simple answer is, we have talked about the cost function. Do you remember? We have talked about the cost function in a normal linear regression. And cost function is nothing but, we have seen it will be equals to 1 by n, summation of I equals to 1 to n. What is the value of y cap minus the value of y of I whole square? That is something that we have discussed as the error or the cost function that we have. I hope you remember that, because in the last session we have discussed this point, right? So here n indicates the number of records that we have, the number of data points that we have in a given sample data, right? So this is something which is the residual sum of square. That is what we have named it in the last session. Now, this is the cost function for a normal linear regression. And because of this cost function only, we are saying that the error term will be approximately equal to 0, right? Because the value of y cap and the value of y of I is almost same. That's why the answer will be 0. In above case, in the overfitting case, what I want is, I want that my training to be going on. I don't want that this cost function or the error value or the RSS value will become 0, right? This is what we want. So what we will do is, there are few techniques that we have. The very first technique is something that we will discuss today, which is called as L2 regularization. So the very first technique which I will discuss today is L2 regularization, which is also called as ridge regularization. What it says is, it says that do one thing. So basically what we're supposed to do, we have seen that in a normal linear regression, the cost function is that RSS value, normal RSS value, which is the difference between the value of y and y cap. So take that as it is, RSS value, which I have defined above, plus lambda times, you will see summation of I equals to 1 to k m of I whole square. Now this k indicates the number of features that we have in a given data, right? Number of columns or number of features, whatever you can say. And this m of I indicates a slope point. Okay? Let's say you will be dealing with the equation of line, which is, let's say y is equals to m1x plus m2x square plus m3x cube plus, let's say you will be having c. Now you know that m1, m2, m3 is the slope values that we have, and c is something which is the intercept that we have, right? C is something which is the intercept that we have. Now we will always try to follow a approach of gradient descent algorithm that we have discussed in our last class, where our target is to achieve a global minima, right? Our target is to achieve the global minima, where the error is minimum, where we will reach to a point where the error is approximately equal to 0. Now, how this equation is helping me to avoid the overfitting? Listen it very carefully. You will observe that when we apply normal RSS, which is this equation, right? Y cap minus yi whole square. In that case, the value will be equal to 0 and my training will get stopped at that point of time for the training data. But what I want is, I am looking for more training per se, because that is not the best fit line which my model is able to get. Because on the test data, it will show a very big number of error. So that is where, now what will happen? I will be having the value. So by the way, lambda is something which we call as hyperparameter. So experimentally it is being chosen hyperparameter depending upon what kind of data set we have. So now what will happen is, we will try to add, apart from, let's say, the value 0 also, we will try to add some value which is bigger than 0. So what will happen is, the training will keep on going, and it will keep on going until it reach to a new global minima, and that is where we will be able to get something different best fit line, which is not the green one but the red one, right? It can be anything, but definitely it will not be equal to 0 in that case. So that is something which we are doing in a L2 regularization or a ridge regularization. Now, when we talk about L1 regularization, there are few things which are exactly same. Again, there is a modification of cost function only. By the way, it is also called as lasso regularization technique. Okay? Lasso regularization technique, the full form of this lasso is list, absolute, shrinkage and selection operator. So let me write it down. List, absolute, shrinkage and selection operator. Now, why it is called as shrinkage and selection operator, what we are doing here, and why it is absolute, you will get to know each and everything. So the cost function here, the modified cost function which we will be able to get in this L1 regularization will something look like this. You will be having a residual sum of squares error, plus you will do again summation of, again, I equals to 1 to k, where k indicates the number of features you have. But here, instead of doing a squaring part, you are trying to add the absolute value of the slope. Now, the difference between this above ridge regularization versus this lasso one is, you will be able to see we are doing an absolute shrinkage. That is, it's called absolute shrinkage. So we are trying to decrease the value again. Let's say you will be having again the RSS value as 0. Again, you will be able to get some value which is bigger than 0, right? So it will not shrink very fast. So you are trying to again penalize that slope values. But here, if you will be able to observe, obviously the value will be much bigger because we are doing a squaring of that as comparable to the lasso value, where we are just trying to find out the absolute sum. Okay. Now, why it is called selection operator? Because this is a technique which is also used for the feature selection per se, which is also useful for the feature selection per se. Okay. Why is that so? Because what is happening is, at each and every point of time, you will observe, by the way, I forgot to mention lambda is also there. So lambda is a hyperparameter, lambda times that summation of I equals to 1 to k absolute value of m of I. That's the correct equation. Now here, if you will be able to observe, what is happening is, at each and every point of time, at every iteration, what will happen? You will be able to see that there is a decrease in the value of m of I. Same thing will happen in the above case also. There will be a decrease in the value of m of I square, right? There is a decrease in the value of m of I square. But in this case, it's a value of m of I. So what is happening is, after few iterations, you will see that for few features, the value of slope, which is m, will be again pointing to 0, is approximately equals to 0. And if for few features, let's say the value of m is approximately equals to 0, where k indicates the number of features, what that indicates? That indicates that those features are not that much important, right? Those particular features, maybe let's say for x2 or for x3, the value of mi is, let's say, 0.0000001. So it's approximately equal to 0 itself, right? In that case, it indicates that those features are not important. So we will try to remove those features, right? So this is something, that's why it is called as feature selection technique. Whatever features are important, for those features, the value of mi will never be equal to 0. But for the features where the importance is very, very less, you will observe that after a few iterations, that value will be approximately equal to 0. And that's where it is also called as a feature selection technique. Now, there is another regularization technique that we have, which we call as elastic net. Again, you will heard this term a lot. Now, whenever we're talking about elastic net, it's not something different with respect to whatever things we have covered up. Let's say you want to reduce the overfitting. Plus you want to specify, you want to do the feature selection part as well, pretty well, right? So in that case, what you can do is, you can take a combination of both of them. You can take a combination of lasso plus ridge. You can take a combination of L1 and L2. And that is something which comes out to be elastic net. So I can say it's a combination of L1 and L2 regularization techniques. L1 and L2 regularization techniques. So what will happen? In this case, you will be able to observe, what we will be able to achieve is, you will be able to see lambda 1, summation of I equals to 1 to k. You will be able to see we are adding m of I, slope value, plus we are doing lambda 2. Again, summation of I equals to 1 to k, the value of m of I square. So we are trying to do the addition of L1 regularization plus L2 regularization to make it a beautiful combination where we will be having all the properties of L1 and L2, where we will be able to take the advantage of both of the applications, feature selection plus overfitting. That is where elastic net will be used. So that is the overall idea behind regularization technique. So now I hope that you got a major clear-cut idea about the regularization techniques. The very first thing, why it is required, that is something which we have learned. Secondly, what are the techniques we have? We have talked about L1, L2, elastic net, the composition of both of them. So each and every technique has its own, advantages. What's its mathematical intuition? Everything we have covered up. So still, if you have any sort of doubt, any sort of confusion, please do try to reach out to me. I will for sure try to resolve it as soon as possible. With this, happy learning to all, and I'll see you all very soon in the upcoming video, where now we will do the implementation of whatever things we have learned so far, right? So if we have seen that how we can implement a normal linear regression, but let's say you have to apply a regularization technique given any data. So first of all, we will try to pick that data where we will see that overfitting is there. And after that, we will try to avoid that via the techniques that we have learned today. Okay? So another amazing session is about to come. So please stay tuned. Bye-bye everyone and see ya.